giving an introduction to the Offshore Renewable Energy Catapult as an organization, and a little bit about how we see hydrogen, and a bit about what my team specifically is doing, which is the electrical research team. And I'll just give you a little bit of my background as well. So I've got a background in chemical engineering. I did a CDT program called ID Core, where I was based at the European Marine Energy Centre, so the next presentation. And I was looking at hydrogen in a few different guises. And from there, I've moved more recently to the Offshore Renewable Energy Catapult as a research engineer. So we'll make a start. So an introduction to the organizations. So it is a leading technology innovation and research center for offshore renewable energy. So it covers a lot of different areas, so research and innovation. We've also got some really impressive testing and validation facilities, and we've also got some people working on analysis and strategy, thinking about, the kind of UK energy system moving forward, what that means in terms of economic impacts for the country. So kind of a wide range of things. To give you a sense of the scale, I'll show a picture here of our Blyth facility. So we've got facilities around the country. This is the main one. So there's a few particular test rigs I'd like to point out. So one is a 100-meter blade test facility. So that was quite big when it was originally built. Now it's almost too small. Blades are now longer than 100 meters. So the end needs to get, if I understand correctly, chopped off, and they put weights on to simulate that extra mass that's been lost. We've also got a 15 megawatt powertrain test facility, which is testing GE's Halide X device. And we can actually link that to an 18 MVA grid emulator system called eGrid. So that's one of the most advanced machines on the planet of its type. And so we can do really sophisticated integrated mechanical electrical tests. So we're able to simulate what these machines are going to see in massive storms while in the cozy building. So that gives you an idea of the kind of facilities of the Catapult. And I'm based in the research side. So an earlier report, one of the early pieces of work that the Catapult did into hydrogen was a report on offshore wind and hydrogen. It was called Solving the Integration Challenge. And it had a really lovely kind of graphical key messages page. So this is an easy one to look at here. So it looked at a few different things that included the kind of opportunity for the UK. So basically it found that at a high level, there is sufficient offshore wind for the UK's energy needs. And there's even sufficient energy such that the UK could set up an export industry. So that's really fascinating, could be really important for the country going forward. It also crunched some of those numbers around the energy system. So it reckons that the UK energy system might require 130 or maybe 200 terawatt hours of hydrogen by 2050. And that helps to integrate 75 gigawatts plus of offshore wind. So, that's the kind of scale of ambition here. It also looked at the cost reduction that we might see of hydrogen. So this will be familiar work, I'm sure, this kind of idea. Basically, the idea is that hydrogen from renewables is maybe a bit expensive at the moment, maybe £5-ish per kilogram, but we're hoping to see a kind of similar scale of reduction as we saw with wind and solar. So that's kind of 80 or 90% over a decade to really get that down to those lower numbers, a couple of pounds per kilogram. And we also looked at comparing that green to blue hydrogen, which we talked about earlier in the session. So that's still a topical question. In addition to these points, we also looked at some of the economics of producing hydrogen from offshore wind, and they looked really promising. So the report found that there was a cumulative gross value added of 320 billion and 120,000 new jobs potential for by 2050, if we kind of think about putting offshore wind and hydrogen together. So a really big prize there. So there's been new developments since then. So there's been a whole raft of hydrogen documents published by the UK and the devolved nations, which you'll be familiar with. There'll just be a few that I'll highlight here. So one is the UK government's 10-point plan. So the offshore wind and hydrogen are points 1 and 2. So these are kind of that highlights the importance of them. We also had this really exciting program called Scotland. So for those who are new to Scotland, basically Crown Estate Scotland said, we've got these patches of seabed, who would like to build wind farms on them? And 74 people got in touch to say, we'd like to build wind farms on them. I think about 17 were selected. and their kind of combined wind capacity, we thought it was going to be about 10. That's what the sector was expecting. And it turned out to be almost 25. So, you know, a lot more ambitious than the sector was expecting. And it raises a whole load of interesting questions. So this is the map. You can see the seabed areas in black outlines, and you can see the wind farms that have been given the green light in green there. So there's one that I'd like to highlight, bring your attention to. So I'll not talk about this too much in case Noor covers it in the next presentation. But this one here is a 2 gigawatt power plant, and as you can imagine, there isn't necessarily a lot of electrical infrastructure at the north of Scotland. So then there's a question of, if we're building 25 gigawatts, or in this case 2 gigawatts of new wind capacity, how do we get that to demand centres? And one of the ways it might be possible to do that is kind of shown by the Flotte hydrogen hub concept. So this is a really fascinating development that you can read about online at this website. But basically the idea is that maybe we want to take some of the electricity from that wind farm and send it to the Spittal substation. And maybe we actually want to send the rest to a new hydrogen facility, a kind of gigawatt scale facility on the island of Flotte, where it could plug into hydrogen export or maritime refueling or a hydrogen pipeline to the Great British Gas Grid. So this isn't something that the Catapult's involved in, EMEC is, but it is kind of one of the things that we're kind of watching and seeing how this space is developing. And we're just seeing how, you know, fascinating this new space is becoming. And in addition to that, just last week, we had the new UK energy security strategy, which raises the ambition for wind and hydrogen even further. So, you know, it's a really dynamic space, and I think we're going to be busy over the next few decades. So, a great big space. How does the Catapult specifically see hydrogen going forward? So as you know, there's loads of research fields that this question spans. We think that the most important for the Catapult, we're still finding out the fine detail, but the basic idea is that hydrogen is important from our perspective as a means to integrate offshore renewable energy into the energy system. So there's a few areas that we might want to focus on. One is on detailed technology studies. So these are really interesting questions like, how can wind turbines be best connected to electrolyzers? That's one. And then there's another one of how reliable are pipelines compared to cables? You know, those kinds of nitty-gritty, detailed technology questions. And linked to that, we're also thinking about if there's a space for new test facilities that we might be able to deploy alongside our existing facilities on Blyth. And you can imagine a kind of lab to ORE to kind of field test facility progression there. So we're really excited to see what we can do in that space. If we move from technology to project economics, we can then start to think about questions like, when does it make sense to include hydrogen in offshore renewables? And should it be produced onshore or offshore? So that's thinking about project economics, and that feeds into things like subsidies, so contracts for difference, feed-in tariffs. I think that's a developing space for hydrogen, so we're looking forward to seeing what's going to come out in that space from the UK government. And then if we take another step to a higher level, we can start to think about energy systems. So with lots of new wind farms coming online, which should be dedicated to hydrogen to optimize the whole system? So there's lots of influencing factors here. These could include the distance from shore. So maybe pipelines are more favorable at longer distances than cables. Maybe we can identify the kind of crossover with some general heuristics to see where one makes more sense than the other. There's also influencing, another factor could be nearby electrical connections. So if there's a large nuclear plant at the coast that's been decommissioned, and that's a relevant scenario for Scotland at least, there's going to be this great big electrical infrastructure with no power supply. And so perhaps it makes sense in that case to have wind farms that export electricity. On the other hand, we might have geological stores such as porous rock media that can store not just terawatt hours, but tens of terawatt hours worth of hydrogen. So if you've got a kind of a great big wind farm beside a porous rock media subsea geological store, maybe you actually just want it making hydrogen which goes straight into the store, and that acts to boost the UK's energy security and around the North Sea as well. And another influencing factor could be demand for chemical fuels. So this could be at ports. So we've talked about ammonia and even liquid hydrogen. Ports, airfields, and industrial clusters, we can imagine, are going to need hydrogen or molecules containing hydrogen. So if a wind farm is near one of those kinds of facilities, perhaps that gives a clear steer on what should be exported. So that gives an idea of the kind of big picture space that we're investigating. We've got some projects that are helping us to progress some of these questions. So one, our flagship project at the moment is the Milford Haven Energy Kingdom project. So Milford Haven is a place in Wales, and it's called an Energy Kingdom, the Energy Kingdom project, because it's a really amazing place for hydrocarbon facilities. So this is one of Europe's largest, most complex oil refineries owned by Valero. This is a 2.2-ish gigawatt gas power plant operated by RWE. I think this is an oil terminal, and we've also got LNG terminals along this north coast. So when it comes down to it, Milford Haven can import 25 or even 30% of the UK's gas demand. So we've got these incredible, petrochemical facilities. And the question that the project is exploring is the potential of renewable electricity and hydrogen to meet future energy needs of a port, in this case, Milford Haven, which has major existing hydrocarbon infrastructure. So this has got lots of different aspects. It's got some hardware on the ground that's basically world firsts or UK firsts. The space that we're more involved in at the Catapult is looking at the longer term energy transition and understanding what needs to happen to enable multi-gigawatt offshore renewable installations in the Celtic Sea and the role that hydrogen can play here. So the Celtic Sea, I hadn't heard of it before I started working on this project. It kind of spans from Ireland to Wales to Cornwall to France, so it's kind of west of the English Channel. And there's potential there for tens of gigawatts of offshore wind. So in the same way that we could see a major rollout in the North Sea, we could also see a major rollout in the Celtic Sea. Cornwall and Wales perhaps don't have the strongest electrical grids like we saw with Scotland, so perhaps hydrogen has an important role to play here. So that's the kind of space that we're exploring. And specifically, we're looking at technology, smart local energy systems, larger demonstration projects, and understanding the role of Milford Haven in the context of a new global trade in green hydrogen. So this project is wrapping up at the end of May, so not long now. So we're kind of furiously trying to get everything rounded off as best we can. So there's going to be lots of interesting documents coming out. Do keep an eye out for those. Amongst those documents, we've kind of engaged in some deep dives. So the first deep dive that we've done is on modeling integrated wind turbine electrolyzer devices. So I mentioned this earlier. So there's lots of interesting technology questions that get raised here. And one is about how much energy the wind turbine will produce that an electrolyzer that's plugged into it cannot use. So there's two main ways that might happen if we say that there's no downstream bottlenecks. One is if we say that we have a 5 megawatt wind turbine with a 5 megawatt electrolyzer, maybe the wind turbine can start producing energy at just a few hundred kilowatts, so maybe 100 kilowatts. But if our electrolyzer, for example, has a minimum load factor of 20%, then it needs at least 1 megawatt before it can turn on. And so all of the wind power between 100 and 1000 kilowatts can't actually be used by the electrolyzer. Another way that we might have wind energy spill is if we have an electrolyzer that's smaller than the wind turbine, and there might be economic reasons for doing that, maybe having it 85 or 90% of the wind turbine capacity. So we might have a 4.5 megawatt electrolyzer with a 5 megawatt wind turbine. And so you can imagine that that kind of top 500 kilowatts will get spilled on a regular basis. So in that kind of case, we want to ask, well, how much energy would actually be spilled? Like, how much is it? Could we store in a battery for standby periods? Or do we want to think about inserting a smaller stack which can soak up power between 100 and 1000 kilowatts? Those kinds of questions. So we can tackle those at a higher level. Some of them we need to go to a deeper level of detail. So for example, if we think about response times, control systems, and requirements for supporting equipment to balance the electrical microgrid. So wind turbines are usually operated at a control scheme called maximum power point tracking. So they're always producing as much power as they can. There's a question there. can the electrolyzer keep up with the wind turbine? So if the electrolyzer can respond instantaneously, then yes, it can. But we know that real machines don't respond instantaneously. So then there's a question of, well, maybe it takes 0.1 seconds, maybe it takes 0.2, maybe it takes 5 or 6. And in each of those cases, you can imagine that we'll need supporting energy storage equipment, maybe a battery, to balance the electrical system. So we can start to do things like plot battery capacity as a function of response time. Alternatively, we can think about the control system. So maybe with maximum power point tracking, we see a maximum power change per second of maybe 200 kilowatts per second. Maybe the electrolyzer can't do that, but maybe if we put a limit on the change rate to maybe 100 kilowatts per second, then maybe the electrolyzer can keep up. So that's a kind of, a huge space to explore in and of itself, and it will change between machines. But that gives an idea. We're also thinking about kind of microgrid requirements for black start capability. So maybe we want a fuel cell, but maybe we also want to have a boost from another battery that just kind of kickstarts everything. We can think about the kind of optimal electrical layout as well, kind of how to connect all these different machines together best. And if we get more into detail, we can start to think about modeling novel power converters and find the benefit to efficiency. So I'll mention that later on in the presentation. So one to bear in mind. A deep dive that we're doing is a safety study. So we're kind of looking at this picture here, this bold new vision, and we're trying to identify what could go wrong. So I'm sure we're going to think of lots of things that could go wrong. Then the question is, can we reasonably prevent those things, or is it a showstopper? So that's going to be a really important question for this new industry going forward. So I'm looking forward to seeing what we can do there. So that's the Milford Haven Energy Kingdom project. That's a small selection of the things that the project has covered. We're working on other projects as well. So you'll be familiar with H105. This is using ORE's 7 megawatt demonstration turbine to power an electrolyzer with the resulting hydrogen distributed in a similar way to natural gas. So that's I think I've got 2 minutes left, Gavin.
2 minutes, yes.
Cool, thank you. So it's this kind of picture here, and we're looking forward to kind of producing some hydrogen with the turbine. We're also involved in the CLEAR project, which is the Smart Energy System project, looking to coordinate the operation of the demonstration turbine I just mentioned, PV, batteries, and potential hydrogen systems to make the most of renewable energy. So we've got PV installations on community centres and some sun-in batteries, and the turbine, we might get access to a hydrogen system when we're looking to orchestrate those as best we can. And one where we've gone into a bit more detail is the Hyperwind project. So in this case, we've been supporting power electronics manufacturer Dynex in a feasibility study for an optimized power converter for, again, integrated wind turbine electrolyzer devices. So today, producing hydrogen or powering an electrolyzer from a wind turbine looks a bit like this. So we start with AC, then we process that by going to DC and then back to AC to meet the grid requirements. And then if we want to get that back to an electrolyzer, we go back to DC again. So a few steps. You can imagine in the future, maybe we want to switch to something that looks like this. No good connection, less steps. So the kind of questions we've asked are where to break into the system. So more novel to remove a lot of the existing system and do something big from scratch, but potentially less attractive to wind turbine manufacturers. There's questions about what the optimal power electronics configuration was. So I think we went for an active front-end converter with a buck or a boost converter in addition. We looked at the cost and efficiency improvements that would give us. And then we're looking to line up a demonstration and think about how we can tie this into Wales hydrogen objectives. So they've got this whole roadmap, and I'll just highlight the production demonstrations. Maybe by 2030, they're looking to see hundreds of megawatts or gigawatt scale production. And that's all from me. Thank you.